So there are many factors, and let's range them by importance, let's say. So I would rate the first one is the task that we need our sensor for. If we need to identify the six-dimensional position of the object with a very high precision, probably 3D scanner is our choice. So first thing you have to look at is your actual application and task. The next thing that goes together is the accuracy and form factor. For example, if you need to measure some surface flatness very precisely, you need some very accurate 3D camera. If you need to detect the position of some raw object really roughly with the accuracy of several centimeters, you can use a less accurate scanner. And as I told you before, the accuracy really depends on the form factor, and form factor depends on the accuracy, and vice versa. And this all is about baseline. So this scanner has large baseline, large field of view, and rather high accuracy. And as I told you before, the baseline is inverse proportional to the scanner error. So the higher is the baseline, the less is the error. And this scanner has also quite a large field of view, but low baseline. That's why the accuracy of this scanner is much lower. But the form factor is good to mount it on a robot arm. And you can hardly mount this one on the robot arm close to the welding torch. The next thing is also connected with the form factor and accuracy, and it's field of view. The field of view must be chosen depending on your specific task. For example, sometimes there is no ability to mount the scanner on the robotic arm, and that's why you have to mount it stationary. And in this case, you can probably use some larger scanner with larger field of view. Also, it depends on the size of the parts you work with. For example, if you have several tens of meters long parts, then probably you want to make as few shots as possible, so you better choose a higher field of view. And if you have just small objects that you want to scan, you can use some smaller field of view and smaller scanner. And as I already said, it all interconnects with the accuracy. So it's not possible to get high accuracy, small form factor, and large field of view. You can have large field of view, large form factor, and high accuracy, or large field of view, small form factor, and lower accuracy. Shooting speed is also very important. For example, in some applications you have to shoot moving objects, and in this case your shutter needs to work really fast, and you need to acquire images really fast that you don't have any kind of deformation and artifacts. But in some cases it's okay to have several seconds per shot. For example, if you shoot static objects, and then the precision can be higher, but the speed is lower. And in some cases the speed is higher, but the precision and accuracy is lower. As for the shooting speed, sometimes if the scanner is mounted on the robot, you want to scan really fast and move the robot really fast, and it requires the camera to be able to shoot in a high frame per second. And in some cases you don't need to shoot while moving, and you can make a shot, move, take a shot, move, and so on. So the next important thing is the housing of our devices. We need industrial housing since we have industrial robots. So for example, this device has a very good housing. It protects from collision, from vibration, from heat, and from dust and dirt. In contrast, this device does not have any industrial housing. It has holes in it for ventilation, and if you put it without any additional case, in some real production site, it will be covered with dust and it will burn down in several weeks, I guess. Another important thing is the wiring interfaces, and they also have to be industrial. For example, here we have M12 Ethernet, which is an industrial standard, and we have another industrial connector here, and it prevents from accidental disconnection of the cables. In case of real production, it's important. Also, another thing that you have to consider choosing the wiring interfaces is that some interfaces, like USB 3, have limitations on the length of the cable. For example, this camera is a USB 3 camera, and this is actually almost the maximum length of the cable. So you need to put your computer somewhere close to the camera, and it can be a big problem. And this camera has a Ethernet connection, and Ethernet can be transmitted up to 100 meters, so it's not a problem for it to have a computer far away. Sometimes another important thing is to have digital outputs and digital inputs interfaces, because you need to synchronize cameras between each other or synchronize camera with the robot. The most frequent example here is the line scanner, where you have to synchronize the profiles with the pose of the robot to get the whole scan of the object while you are moving the scanner along the object. So imagine that my arm is a robotic arm and that I'm moving the scanner and shooting the profiles of this object. In this case, I need to know the pose of the robotic arm for every profile I get, to stitch them all together and to get a beautiful 3D point cloud of my object. And for this, the best way is to use digital output of the robot or digital input of the sensor, or vice versa, to synchronize the signals. And the last but not least is the software API. The software API is actually our tool to interact with these devices, because without good software API, we cannot acquire data, we cannot process it, we cannot do it fast, and so on. And another important thing, that the API should be supported by the vendor and get updates and so on. Actually, there are two kinds of calibration: intrinsic calibration and extrinsic calibration. Intrinsic calibration is the calibration of the internal parameters of the camera, and it influences the accuracy of the device itself. Usually, the vendors do not give access to intrinsic calibrations, and in many cases, if you broke down your device, you just send it to the vendor and it makes recalibration. But some vendors gives you access through the API to the intrinsic calibration, and if something goes wrong, you can simply recalibrate your camera. The extrinsic calibration is actually the position of the camera in some real-world coordinate system. And it's really important to interconnect coordinate system of the camera with some world coordinate system where you make your measurements in. For example, in our application, we have a robot. Somewhere we have a camera. And we have an object here. So this camera shoots the object, gets the point cloud, and actually it gets the point cloud in its own coordinate system, because it doesn't know anything about the robot. And the extrinsic calibration is actually the way to recalculate the position of this. For example, we detected this object and it has this position. And this pose. And this pose is in coordinate system of the camera. And we need to calibrate the camera along with our robot. Usually it's some robotic base, for example, this coordinate system. So knowing the position, the coordinate system of this camera with respect to the base of the robot is called extrinsic calibration. In industrial robotics, for robot arms, there is a special kind of extrinsic calibration called hand-eye calibration. For example, if we have our robot and the camera installed on it, we know in every moment of time the position of the flange of the robot, but we don't know the transformation between the flange of the robot and our camera. And there is a special procedure how to get this transformation. So we can put a calibration object here and shoot it from different poses. Then storing the position of the flange and the position of the object in every image shot from these positions, we can recalculate this transformation from the flange to the camera. And this procedure is called hand-eye calibration. The accuracy is actually one of the most important parameters. And the funny thing is that it has a really difficult definition. So there is no single definition of accuracy. Every vendor defines it the own way, and vendors don't like to put specific values in their specifications because actually the problem of accuracy is really complicated. And now I'll try to explain how to measure the accuracy of the 3D scanner. The first one is the depth map resolution. Actually, it defines the number of points, of depth points that you actually get from your scanner. And it equals the resolution of the sensor metrics that you have inside your device. For example, if you have 1024 by 1024, it means that with one shot you'll get approximately 1 million points. The next parameter that is frequently used is point size. The point size is actually the distance, the average distance from neighboring points in an average point cloud shot by this device. This parameter is also sometimes called pixel size, and it's connected with pixel size, and pixel size means the actual length in the real world that is projected to the single pixel of the device. This parameter can be measured at different distance from the device to the object. It can be in the center of the field of view, so-called sweet point, or further or closer, and it depends actually on the distance from the device. The next important parameter is the Z accuracy, and Z accuracy is the actual accuracy of the device. So the difference between the distance to the specific point and the ground truth distance of this specific point. The Z accuracy is usually averaged over the whole imaging plane, and it also depends on the distance from the scanner. So further away, the Z accuracy is lower. There are multiple definitions of Z accuracy. Sometimes it's signed, sometimes it's measured as a magnitude. It all depends on the vendor. So the next parameter is spatial noise. Spatial noise is the deviation of error along the region of interest of the camera. Usually it's measured by putting some plane in front of the camera and measuring the error in every point of this plane. And then we just calculate the standard deviation or something like that to estimate how error deviates in different parts of the region of interest. The next important parameter is temporal noise. Temporal noise is actually stability of the measurements in time. Usually it's measured by taking several shots one by one and measuring the error in the same points in space and calculating the deviation of the errors in time. The next parameter is calibration accuracy. And calibration accuracy is not provided by all vendors, but provided by some. And it's actually the most integral parameter that can be measured, and it can be understood as space deformation in the eyes of the device. So it is measured as an average error in different space points in the field of view of the device, and actually defines how good and how deformed is the point cloud that is acquired by the specific device. Since there are so many parameters, usually the vendors just put some general accuracy in their datasheets, and they usually write something like the accuracy is 1% of the distance from where you shot the object. And it's a good estimate, but it's not really convenient for developers like us because it's hard to understand the real accuracy of the camera. The short answer is yes. Most likely yes. AI will outperform all the algorithms, and it is already outperforming most of them. I won't say that 99% of computer vision algorithms, but more than 90, I guess, nowadays is machine learning based algorithms. But still, there are a couple of notes to mention. First, the progress in machine learning is enormous in the last decade. But as I already said, not every task can be solved using the machine learning algorithms. And for some tasks, the combination with old school mathematics works really better than pure machine learning. The second thing is that machine learning is learning after all. So it has to learn from something, and someone needs to teach the algorithm. And in case of computer vision, we are talking about data. So the more data we have, the better our algorithm performs. And it's not only the data itself. The data should be marked up. So it should be accompanied with some ground truth that is created with some human. And the data set should be really diverse and should be really large. And this problem of the data doesn't seem to go away in near perspective, even though there are some few-shot learning, interactive learning, weak supervision algorithms are developing nowadays, and it's very popular. But I still think that the existence of good data is the cornerstone in the performance of machine learning algorithms. Actually, many devices are already better than the human eye, but human eye is accompanied with the human brain, which is so far the most powerful cognitive device in this world. So, of course, we need good algorithms to go along with the good sensors to solve problems in robotics. Next, even though there is a great progress in sensor technology, there are still quite a lot of some classic problems with data quality in almost all of the sensors. And mostly these problems come from the real-world environment and the complexity of the world that we live in. The problems are like reflective materials, different ambient light, outdoor environment, some transparent materials, and so on and so on. I think that there is a huge progress in solving these problems, and many of them will be solved in the near future, but some of them will be not solved still. I would imagine an ideal device in a couple of years as really compact with a large field of view, great accuracy, and the ability to shoot in real time, and at the price level of $100. and of course a very powerful AI algorithm that can solve any task I will ask it. So thanks for watching till the end. We appreciate your feedback. Please write in your comments if there are any questions that were not answered in this video. Bye!